What does Saturn hide? Today, we journey to a world of rings and mist, a place where time stretches and beauty mingles with the strange. Saturn, more than a planet, a majestic enigma. From ancient augurs to the orbits of probes, it mesmerizes, it questions, it reigns in silence. What do we truly know about this Lord with golden rings? And why, in the infinity of the cosmos, have we fallen under its spell? But before we embark on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a good trip. We are transported 1,500 years before our era to Mesopotamia. The Babylonians, masters in sky observation, scrutinize a discrete star they call the Star of Ninurta, in honor of a protective and warlike deity. On the MUL Apine tablets, they record a cycle of about 378 days, used as a reference to predict certain events, although it differs from the star's actual path. Through these celestial movements, they seek divine signs, convinced that Saturn influences the course of the world. In ancient Greece, the same planet is named Kronos, the master of time, father of the gods of Olympus. The Greeks draw on Babylonian knowledge to structure the calendar of their rituals. When Rome rises to power, Kronos becomes Saturnus. The Romans, passionate about stars and symbols, celebrate the Saturnalia, grand festivals where social roles are reversed. Already, the planet's slowness embodies the permanence of time, the unchanging rhythm of seasons and beliefs. Latin poets describe it as a fixed point at the edge of the known sky. Easily visible to the naked eye, Saturn shines moderately, less than Jupiter or Venus, but sufficiently to attract gazes. Its slow movement is explained by its long revolution, nearly 29 years to orbit the Sun, more than a human generation. Thus, it seems fixed from week to week. In antiquity, this slowness is perceived as the reflection of a stable force, a silent wisdom acting through the ages. A decisive leap occurs in the 17th century. In 1610, Galileo points his telescope towards Saturn and sees strange extensions on either side of the disk. He still does not know he is observing rings. The quality of his instruments does not allow him to discern their shape. He notes their temporary disappearance, which leaves him perplexed. In his writings, he speaks of a planet with a changing face, without finding an explanation. In 1655, Cassini-Huygens dispels the mystery. He understands that Saturn is surrounded by a thin ring detached from the planet. He also discovers Titan, a colossal moon he first identifies as a star. This body, larger than our moon, reveals the extent of the Saturnian system. Huygens guesses this system hides many more surprises and already questions the possible existence of an atmosphere around Titan. "20 years later, Giovanni Domenico Cassini observes a dark band dividing the main ring. It will bear his name. In the same year, he discovers Iapetus, a moon remarkable for its luminous contrast. Thanks to better telescopes, he also identifies Rhea, Tethys, and Dione. These worlds show striking diversity, with varied, sometimes very pale reflections. These observations fuel the debate about their origin, some imagining a joint formation with the planet. In 1789, William Herschel, equipped with more advanced mirrors, detects Mimas and Enceladus. Their faint brightness does not prevent him from confirming the abundance of satellites around Saturn. He also tries to measure its rotation, which he estimates at just over 10 hours. An astonishing speed for such a massive globe, reinforcing the idea that the planet is made of gas in perpetual motion. But the measurements remain approximate as the cloudy surface spins at variable speeds, making analysis tricky. In the 19th century, spectroscopy becomes a central tool to uncover Saturn's secrets. Traces of ammonia reveal the presence of volatile gases. In 1856, James Clerk Maxwell demonstrates that a solid ring cannot hold. It must be formed of a myriad of particles. This revelation explains the system's stability and sheds light on the distribution of matter around a giant planet. Some astronomers begin to think that the rings might be the remnants of ancient celestial bodies disintegrated. Photography, booming at the end of the century, allows for capturing images of Saturn. The first plates show details of the rings and the position of several moons. These pictures fascinate the public and offer scientists new tools. They study the shadows, the reflections, and seek to understand the forces that stir the system. Ideas abound. Some speak of tiny collisions, others of constantly renewed dust. The rings then appear as a dynamic phenomenon in constant evolution. In the 20th century, radio astronomy is born with the accidental detection of waves from the sky. Saturn proves to emit thermal signals, indicating inner heat. This discovery challenges the idea of a cold and inert world. Researchers suspect mechanisms such as gravitational compression or helium migration to explain this energy. Laboratories attempt to reproduce these conditions, exploring the circulation of gases deep within. Shortly after, photometry refines the understanding of the rings. By measuring their light, researchers observe that their inclination varies. Every 15 years, they become almost invisible when seen edge-on from Earth. This phenomenon fascinates both scientists and the curious. These rare moments are used to scrutinize their structure. Measurements reveal areas of varying density, influenced by nearby moons, creating complex patterns and waves in the material. By 1955, the face of Saturn has slowly been unveiled, from Babylonian omens to the major discoveries of Cassini and Maxwell. The rings, once enigmatic, are recognized as a cloud of debris in orbit. Galileo, Huygens, Herschel, and others have uncovered a complex system of moons and movements. Tools like spectroscopy and radio astronomy have revealed a turbulent atmosphere and mysterious depths. On the eve of large-scale space missions, Saturn is no longer just a light in the sky. It becomes a world of its own, full of promises and mysteries to solve. At the very beginning of the space age in 1957, the launch of the first artificial probe named Sputnik marked the start of a true race to the stars. At that time, geopolitical tensions drove the great powers to push technological boundaries, and the mere act of sending an object beyond Earth's orbit seemed almost legendary. Sputnik, a small Soviet satellite emitting simple radio signals, might not seem spectacular compared to today's technologies, yet it revolutionized perspectives by proving that humanity could truly cross the boundaries of our world. From then on, scientists embarked on a frantic quest to design more reliable rockets, more precise communication systems, and increasingly sophisticated navigation protocols. In parallel, the desire to explore distant worlds became more pressing. Astronomy enthusiasts, previously limited to naked-eye observation or telescopes, began dreaming of devices capable of reaching the farthest planets in the solar system. Among them, Saturn, already fascinated with its majestic rings, still largely misunderstood. Known since antiquity, Saturn yet remained a mystery. It was known to belong to the family of gas giants, less massive than Jupiter, but much larger than rocky planets like Earth or Mars. Its rings, identified through early modern observations, were subject to much speculation. Were they composed of solid disks, fine particles, ice, or rock? The ambiguity persisted. American and Soviet space programs competed in creativity for each new step, with the ambition of one day sending probes far enough to solve these mysteries. Meanwhile, engineers improved engines, refined tracking techniques, and developed calculations necessary for interplanetary travel. These advances, fueled by the momentum born from Sputnik's launch, were essential to consider leaving Earth's orbit and venturing towards Saturn. In the 1960s, NASA's priority was clear: reach the moon. The Soviet Union, on its side, was pursuing its own program. All media attention was focused on these moon landing attempts, spacewalks, and the first images of the far side of our satellite. Yet, in the shadows of these achievements, a small group of researchers was preparing probes designed to explore the edges of the solar system. These were the Pioneer and Voyager missions, conceived to study Jupiter first, and then, if conditions allowed, to venture towards Saturn. The dangers were unknown: radiation belts, particle flux fatal to electronics. Nothing was ruled out. Instruments had to be protected, and antennas designed capable of transmitting clear signals over billions of kilometers or miles. A real technological challenge. Among the first attempts, Pioneer 10 paved the way in 1972 by flying by Jupiter. A year later, Pioneer 11 followed the same path with the mission to approach Saturn. On board, a set of instruments aimed at measuring the magnetic field, analyzing particle composition, and capturing the light emitted by the planet. A magnetometer, proton, and electron sensors, all designed to withstand extreme radiation levels. If the probe managed to cross Jupiter's hostile environment, it could then contemplate a historic encounter with the ringed giant. In 1974, Pioneer 11 crossed Jupiter's orbit and collected valuable data, such as mapping certain storms and measuring radiation fields. Engineers decided to use Jupiter's gravitational force to alter its trajectory and propel it towards Saturn. This technique, called gravitational assist, allowed an increase in speed without consuming fuel. Thanks to this feat, Pioneer 11 embarked on a journey of over 5 years to the ringed planet. On Earth, scientists refined their predictions. The probe risked passing through debris zones. A miscalculation, a single too massive fragment, and the mission could fail. Tension was palpable as Saturn approached, where every trajectory adjustment had to be absolutely precise. Finally, in 1979, Pioneer 11 reached Saturn and achieved an unparalleled feat. One of the most spectacular moments was crossing the F ring, one of the thinnest and most mysterious. Before this passage, the A, B, and C rings were known, but the F ring, irregular and barely visible, remained largely unexplained. Engineers feared an impact with a fragment. However, the probe traversed this zone without incident and collected unprecedented data. It revealed the existence of knots and irregularities, showing that the rings were far more complex than simple disks. The cameras, rudimentary for the time, sent back images that would mark a turning point. For the first time, this fascinating system was closely observed. Pioneer 11 also succeeded in measuring Saturn's magnetic field. The results were astonishing. It was about 600 times more powerful than Earth's. To better understand, it is worth recalling that Earth's magnetic field protects our atmosphere from solar particles. Saturn's, on a much larger scale, generates an immense magnetosphere capable of diverting the solar wind. These data allowed new hypotheses about the planet's interior. Such a strong magnetic field suggests an active core, producing electric currents through conductive fluids. This mechanism, known as the dynamo effect, is at the heart of many planetary theories. Another major advancement was the detection of the bow shock. This shock wave formed when the solar wind hits the magnetosphere. This phenomenon, comparable to the wave formed at the front of a ship, is essential to understand. It allows the measurement of the interaction between the solar wind and a planet's magnetic barrier. Thanks to Pioneer 11, researchers were able to approximate the location of this wave around Saturn and evaluate the shock's strength. This opened new comparisons with observations made around Earth and Jupiter, refining the understanding of gas giants facing particles from the Sun. Beyond this shock wave, Pioneer 11 also detected the presence of energetic particles previously unknown around Saturn. Protons and electrons at very high speeds formed a complex charged flow. This discovery suggested the existence of acceleration mechanisms similar to those observed in the Earth's radiation belts. But their origin remained uncertain. Solar emissions, Saturn's atmosphere, planetary storms. These questions required years of analysis, but Pioneer 11 laid the groundwork by capturing the first clues of intense activity. This mission, from its launch in 1973 to its flyby of Saturn in 1979, embodied the audacity of a generation. In 20 years, humanity had progressed from the first signals of Sputnik to the exploration of a distant world. The passage through the F-ring, the measurement of the magnetic field, the discovery of the bow shock, all were milestones that would feed future missions. For the first time, a probe had approached Saturn, had braved the risks, and brought back a treasure trove of information. It was the joint work of engineers, scientists, and visionaries who pushed the boundaries of the possible. Pioneer 11 proved that Saturn was no longer just a point of light in the sky. It became a world unto itself, vibrant and complex. The flyby of Saturn marked a key milestone. In 2 decades, we had moved from exploring Earth's orbit to direct contact with a planet located hundreds of millions of kilometers or hundreds of millions of miles away. New questions emerged. How is this magnetic field generated? Why do the rings not disperse? What are the origins of these energetic particles? Buoyed by this success, engineers already began to imagine missions capable of entering orbit around Saturn, or even reaching its moons. But before diving into the future, there was time to savor this moment. Saturn was no longer an unknown. Pioneer 11 had just paid it a visit. The photos, modest by today's standards, were a revelation at the time. Thus, from Sputnik to Pioneer 11, barely 2 decades had passed. And yet, everything had changed. These 2 milestones demonstrated that human will, when allied with science, can transform a dream into reality. Thanks to Pioneer 11, it became clear that interplanetary exploration was possible, and that it could even provide data capable of altering our understanding of the cosmos. The passage through the F-ring, the detection of a powerful magnetic field, the discovery of the bow shock, all were significant steps. Saturn was revealed as a world unto itself, reigning over a turbulent space where solar winds, electromagnetic fields, and invisible particles intertwine. This first flyby opened a new era. It sealed the transition from curiosity to exploration, paving the way for the next probes, ready to venture further and further. At that time, between 1957 and 1979, humanity had broken free from Earth's gravity to gaze into the unknown. While the spotlight was on the moon, it was the patient efforts of technical teams that made this advancement towards Saturn possible. Each signal transmitted by Pioneer 11 brought humanity a little closer to understanding the gas giants. The mysteries of the rings, the atmosphere, and the magnetic field were no longer out of reach. In any case, the Sputnik era, elegantly concluded by the adventure of Pioneer 11, showcased a new paradigm. Space exploration no longer had defined limits. In the span of 20 years, humanity had moved from a simple radio beep to delving into the heart of a distant planet's rings. This feat, unthinkable a few years earlier, showed that the boldest dreams can become the foundations of our knowledge. Pioneer 11 was an indefatigable scout, overcoming obstacles one by one to sow the seeds of new science. The unexpected F-ring, an immense magnetic field, a cosmic shockwave, all discoveries that would transform our vision of Saturn. At the turn of the 1980s, two space probes named Voyager 1 and Voyager 2 are about to achieve an unprecedented feat, crossing the outer frontier of the solar system to reach Saturn, the gas giant. Launched in 1977, these sophisticated machines carry a range of instruments designed to analyze the atmosphere, magnetic fields, and particle environments around the giant planets. For many scientists, their passage near Saturn may finally unlock the secrets of this long, mysterious celestial body, famous since ancient times for its bright rings visible from Earth. Yet no one can predict with precision what Voyager's lenses and sensors will reveal. In November 1980, Voyager 1 reaches Saturn's outer orbit and begins transmitting images of unprecedented clarity. Researchers then discover swirling cloud formations in the upper atmosphere, revealing complex meteorological dynamics. As it approaches, the probe also detects variations in the magnetic field, indicating the intensity of the magnetosphere surrounding the planet. Composed of electrified particles held by an immense magnetic field, this envelope acts as a shield against solar winds. Gradually, the images reveal the fascinating aesthetics of the rings, made of countless fragments of ice and dust, shimmering in the sunlight. Among Voyager 1's major discoveries are the powerful storms shaking Saturn's upper atmosphere. These phenomena take the form of giant vortices, sometimes larger than Earth, accompanied by extremely fast winds. In some regions, gusts exceed 1,600 kilometers per hour, or 994 miles per hour, making Saturn one of the most turbulent worlds in the solar system. Lightning is also observed, signaling violent storms. A surprise for scientists, as in this world lacking a solid surface, the mechanisms behind these events remained obscure until then. Another striking phenomenon appears at the North Pole, a hexagonal cloud structure captured by Voyager's cameras. Spanning several tens of thousands of kilometers or tens of thousands of miles, this geometric figure amazes with its stability, seeming motionless on the surface of a rapidly rotating planet. Researchers believe it to be standing waves generated by differential speeds in atmospheric currents. Unlike terrestrial cyclones, this structure impresses with its rigorous symmetry. Voyager 1's images allow for a remarkable examination of its boundaries, offering a unique planetary scale spectacle. As the mission continues, other discoveries enrich the observations. New rings, previously unsuspected, appear. The G ring, more discreet, and the much more extensive E ring eluded ground-based instruments. The F ring, already spotted, reveals unexpected shapes such as braids and moving interlaces. These patterns would be due to the gravitational influence of nearby small moons, capable of guiding orbital matter and causing visible disturbances in the ring structure. In August 1981, Voyager 2 enters Saturn's domain, extending the discoveries of its predecessor. Despite the short interval between the two flybys, this new mission confirms and completes many observations. Its more recent instruments allow refined measurements of temperature in the upper layers of the atmosphere. The data indicates about -130 degrees Celsius or -202 degrees Fahrenheit on average, with slight variations in zones stirred by the planet's internal heat. This heat, partly resulting from the progressive separation of helium and hydrogen, fuels atmospheric activity. Voyager 2 also pays particular attention to the G and E rings, clarifying their structure and composition. The cameras send close-up views detailing the distribution of ice and dust blocks. Through colored filters, researchers perceive subtle nuances, indicating possible impurities like silicates or organic compounds. Spectral measurements confirm a strong presence of frozen water, suggesting that the rings could originate from ancient icy bodies, captured and then fragmented by Saturn's gravity. Beyond the rings, Voyager 2 continues exploring the atmosphere to verify previously identified lightning. Instruments record electrical signals and light flashes that confirm the presence of intense storms. These discharges suggest that deep layers of the atmosphere become electrically charged due to vertical movements, thus generating lightning. On our planet, water vapor plays this role. On Saturn, ammonia and water, though present in smaller amounts, seem to mix in the complex processes responsible for these spectacular lightning strikes. The exploration carried out by Voyager does not stop there. Several small moons are also revealed. Among them, Atlas, Pan, Prometheus, and Pandora draw attention due to their close interactions with the rings. Atlas orbits near the edge of Ring A, where it locally modifies the distribution of particles. Pan, located in the Encke division, influences the empty space it occupies. Prometheus and Pandora, meanwhile, are nicknamed shepherd moons. Their joint presence shapes the contours of Ring F. These discoveries reinforce the idea that the structure of the rings is based on the gravity exerted by these discrete satellites. The appearance of these moons raises new questions: their origin, their precise role in the stability of the rings, and their relative youth on a cosmic scale. They may have resulted from ancient collisions that fractured larger bodies. Their gravitational effects, by creating resonances, would help maintain the cohesion of the whole. Thanks to the collected data, Voyager 1 and Voyager 2 have thus highlighted the subtle mechanisms governing this complex system. Saturn then reveals itself as a teeming world where immense storms, electrical phenomena, and discrete moons shape the planetary architecture. Since the early 80s, Saturn has gradually unveiled new secrets thanks to advances in observational technologies, especially in the infrared. At that time, astronomers took a leap forward in exploring the ringed planet by using ground-based telescopes capable of examining its atmosphere with greater precision. The detection of infrared radiation expanded the field of analysis, enabling the observation of cloud layers, temperature variations, and air currents at different altitudes. In parallel, a method called radio occultation was implemented to probe the internal structure of the clouds. It involves sending and receiving radio signals passing through Saturn's atmosphere to measure its opacity, composition, and density. This was a decade of promising strides, from the mid-80s to the mid-90s. As early as 1982, several observatories endeavored to characterize Saturn's zonal winds, these atmospheric circulations that traverse the planet by latitude, sometimes from west to east, sometimes in the opposite direction. Their speed can sometimes exceed several hundred meters per second, or over 1,000 feet per second. Measurements published during this period reported values reaching 500 meters per second, or 1,640 feet per second. By comparison, on Earth, the most powerful currents at high altitudes peak around 180 meters per second, or 591 feet per second in extreme cases. Such a difference illustrates the magnitude of Saturn's climate system, driven by its rapid rotation, immense volume, and the particular composition of its atmosphere. To analyze these winds, astronomers combined visible and infrared data. By tracking the movement of certain cloud structures, they determined the speed of the currents while evaluating the corresponding temperatures, with infrared revealing the heat emitted by different atmospheric layers. This approach has made it possible to better understand the thermal contrasts that accompany the winds, unveiling a more complete portrait of the atmosphere invisible to the naked eye. In 1986, researchers highlighted another analysis leverage, radio occultation. When a signal passes behind Saturn, it undergoes alterations due to the atmosphere. By comparing signals before and after they traverse, scientists can deduce the vertical structure of the clouds, drawing profiles of pressure and temperature at various altitudes. This tool has become essential for deepening the understanding of the phenomena hidden beneath the visible surface. Thanks to these data, atmospheric models have gained in precision and revealed mechanisms sometimes imperceptible to the telescope. Observations made from the ground have also highlighted major climatic events. One of the most notable was the gigantic storm that occurred in the mid-1990s, around 1990. A storm of such magnitude stretches over several thousand kilometers or miles, marked by a vast bright cloud formation, sometimes visible with amateur instruments and accompanied by violent electrical disturbances. During this event, masses of moisture-laden air rose, forming thick clouds generating energy-laden storm cells. Captured in the visible spectrum, this storm was primarily examined in infrared, where the warmest and coldest areas revealed powerful convective movements. Although rare, such storms occur often enough to be considered an essential component of Saturn's meteorological dynamics. To further the analysis, scientists have attempted to identify the constituents of the clouds and their depth. Saturn features different layers of clouds, composed notably of ammonia, hydrogen sulfide, and water, each appearing at distinct altitudes. Ammonia forms in the coldest layers, where the temperature can drop to minus 150 degrees Celsius, or minus 238 degrees Fahrenheit. Lower down, increased pressure and higher temperature allow water to condense, forming denser clouds. This tiered structure is also found in Jupiter, another gas giant with comparable characteristics. But in the 1980s, and even more after the observation of the 1990 storm, instruments showed that electrical activity within the water clouds was far more intense than previously imagined. As it rises, water vapor can generate strong electrostatic charges. Radio sensors recorded very powerful signals, indicating sustained electrical activity. These results suggest that water clouds play a major role in energy exchanges and the planet's internal dynamics. To accurately assess the depth of these layers, scientists have relied on temperature, measured in infrared, and pressure, estimated through radio occultation. Ammonia clouds appear in zones ranging from minus 180 to minus 150 degrees Celsius, or minus 292 to minus 238 degrees Fahrenheit. As for water clouds, They form at altitudes where temperatures can range from -50 degrees Celsius or -58 degrees Fahrenheit to levels near the freezing point. The enormous pressure prevailing at these depths allows water to remain liquid or in droplet form, despite temperatures well below those observed on Earth. As instruments gained sensitivity after 1990, they allowed for a deeper chemical analysis of the atmosphere. Infrared light, absorbed and re-emitted by different compounds, reveals the presence of certain elements through their spectral signatures. Thus, ammonia is recognized by particular absorption bands, just like water. By comparing these spectra, researchers can establish a very fine chemical mapping of the upper layers. Radio occultation, in parallel, allows for precise localization of the altitudes of these clouds. Together, these approaches have paved the way for an unimaginable three-dimensional representation of Saturnian weather before. By the mid-1990s, accumulated data made it possible to design global models explaining the origin of zonal winds and storms. One of the decisive factors lies in the thermal differential between the deep layers and the upper atmosphere, coupled with heat flows from the planet's interior. Unlike Earth, Saturn produces substantial internal energy. This heat rises, warming the gases and fueling the winds. Meanwhile, solar radiation varies according to latitude and seasons, causing temperature contrasts. These internal and external influences combine, triggering intense atmospheric circulations and violent phenomena. From launch to discovery, the period from 1997 to 2017 marked one of the greatest space odysseys around Saturn. At the helm was the Cassini-Huygens mission, an international collaboration involving the American, European, and Italian space agencies. This ambitious venture aimed to study the gas giant, its enigmatic rings, and its many moons in depth, including Titan, the largest. Equipped with an orbiter named Cassini and a lander called Huygens, the mission sought to unveil the forces at work in the rings, the elements composing Saturn's atmosphere, and signs of geological activity on its moons. From the outset, the scientific team set clear and bold objectives, made possible by the cutting-edge instruments aboard this space crew. Launched in October 1997, Cassini-Huygens embarked on a multi-year journey through the solar system. To reach its destination, the probe leveraged the gravitational assistance of several planets such as Venus and Earth to boost its speed without depleting its fuel reserves. This cosmic ballet was calculated with extreme precision. After nearly 7 years of travel, Cassini entered orbit around Saturn on July 1, 2004. This crucial moment required a perfectly executed maneuver, igniting its main engine to slow down enough to be captured by Saturn's gravity. Failure would have meant the probe would be irretrievably lost in deep space. Once in orbit, Cassini began a rigorous exploration of the planet, its magnetosphere, and its retinue of moons. Trajectories were designed to allow close flybys of the rings, diverse moons, as well as optimal observation of the poles and equator. From the first orbits, the instruments detected powerful storms, unexpected hues in the clouds, and complex interactions between Saturn and its satellites. Simultaneously, precise measurements were taken of the atmosphere's composition, temperatures, and internal layers. Each discovery confirmed the unsuspected richness of this distant world, encouraging the team to go further. But one of the highlights of the mission was undoubtedly Huygens' arrival on Titan. This mysterious moon intrigued astronomers due to its thick, nitrogen-dominated atmosphere and chemical conditions reminiscent of early Earth. On January 14, 2005, Huygens detached from Cassini to begin its descent through Titan's haze. This historic dive, lasting less than 3 hours, concluded with a gentle landing. During this sequence, the probe gathered valuable data on pressure, winds, and air composition. Its cameras sent back stunning images, a landscape dotted with ice pebbles and dry riverbeds, remnants of past liquid flow. These elements quickly led scientists to investigate the nature of these liquids. Observations showed that the seas and lakes on Titan, concentrated around the poles, were composed not of water, but of liquid methane and ethane. Such a composition is possible due to an extremely low surface temperature, close to 190 degrees or 310 degrees, which prohibits the presence of liquid water. This discovery profoundly challenged preconceptions about organic chemistry outside Earth and opened new perspectives on the potential existence of life forms based on other solvents. Meanwhile, Cassini broadened its attention to other moons. Enceladus, in particular, captivated the scientific community. This small icy sphere, about 500 kilometers or 311 miles across, revealed impressive geysers of salty water escaping from its southern polar region. Instruments identified vapor, dissolved salts, and organic compounds in these plumes, suggesting the existence of an ocean hidden beneath its icy surface. This configuration, coupled with signs of geothermal activity, hinted at an environment conducive to the emergence of life. Such revelations strengthened the hypothesis that the outer solar system might host habitable worlds. Cassini did not only explore Saturn's moons, it also enhanced our understanding of Saturn's rings. Thanks to its precise observations, the probe mapped their structure in detail, measuring density, composition, and thickness. The images revealed waves of density and resonance caused by the gravitational influence of nearby moons, which stir these particles like a celestial choreography. Over the years, the mission challenged existing scenarios about the origins of the rings. Some clues suggest they may be younger than previously thought, possibly resulting from the disintegration of an ancient satellite. The mystery remains, fueling debates within the scientific community. In 2017, after more than a decade of discoveries, Cassini began the final act of its mission, the grand finale. This daring phase involved 22 unprecedented passes between the planet and its rings, in a region yet unexplored. The objective was to collect new measurements of the gravitational field and the internal composition of the rings while capturing exceptionally beautiful images. These final orbits refined the estimates of the mass and age of the rings, suggesting a more recent origin than expected. On September 15, 2017, the probe deliberately burned up in Saturn's atmosphere, bringing this scientific epic to a close. A magnificent conclusion to a mission that redefined our perspective on one of the giants of the solar system. Between 2018 and 2021, the scientific community focused on the meticulous analysis of the last data transmitted by Cassini, the probe that had observed Saturn for over 13 years straight. This so-called Post-Cassini phase offered an unexpected wealth of information about the composition, probable lifespan, and uncertain fate of the planet's rings. Following the grand finale of 2017, when the probe deliberately burned up in Saturn's atmosphere, researchers inherited an immense corpus of measurements, revealing particularly the complex interactions between the rings and Saturn itself. Among the most remarkable discoveries of this period is a phenomenon nicknamed ring rain. Behind this evocative name lies a surprising process. Particles from the rings are attracted by the planet's magnetic field and end up entering its upper atmosphere. This flow is primarily made up of water, accompanied by organic compounds and larger particles. Thanks to the instrumentation on board Cassini, particularly the INMS mass spectrometer, scientists identified the nature of these elements by analyzing the gases and dust captured during the final flybys. Their goal, to determine the amount of transferred material and its influence on Saturn's atmospheric chemistry. This phenomenon originates from the strength of Saturn's magnetic field, generated by the planet's internal activity and its envelope of liquid metal. The particles forming the rings, subject to various forces, undergo collisions and sometimes intersect the path of micrometeorites. These tiny fragments, from the depths of the solar system, strike the ice grains and alter their trajectory. Gradually, this mechanism favors their precipitation toward Saturn. It is the combination of these impacts and magnetic influence that sustains this permanent rain of material. For a long time, scientists have sought to date the formation of the rings. An old theory suggests they could be as ancient as the solar system itself, formed during the condensation of the primordial nebula. According to this scenario, Saturn would have captured or generated early on the particles that compose them. Another, more recent hypothesis argues for a much later formation, perhaps triggered by the destruction of an icy satellite, shattered by a collision, or the planet's gravitational forces. This idea has gained credibility over time, especially because the bright appearance of the rings seems to suggest a relatively recent origin. At the end of Cassini's final dive, researchers compared these two hypotheses by utilizing the data collected by the probe. The INMS mass spectrometer played a central role in identifying the exact composition of materials falling into the atmosphere. By comparing the concentrations of water, heavy compounds, and organic matter, it became possible to better understand the exposure duration of these particles in the spatial environment. High levels of certain components could indicate a long history, whereas relative purity might suggest more recent youth. But the results remain contrasting. According to some studies reported in scientific publications, the constant impacts of micrometeorites could give the illusion that the rings are younger than they actually are. Their continuously renewed surface could mask a much older origin. Conversely, other analyses suggest that a recent formation remains more credible because ice particles degrade quickly and should show more signs of wear if they had existed for billions of years. This debate illustrates the complexity of studying these celestial structures and the difficulty in reconstructing their chronology. The term micrometeorite can be confusing. It does not refer to fiery rocks visible in the sky, but to tiny grains, sometimes smaller than a millimeter, 0.04 inches. Present throughout the solar system, these invisible projectiles constantly strike exposed surfaces, including the particle clouds forming the rings. This discrete but relentless rain modifies the chemical structure and matter distribution over centuries. Hence, the impact velocity and density of these particles become essential parameters for understanding the evolution of the rings and their potential renewal. During this research period, scientists also evaluated the mass loss of the rings. Like a dwindling stream, these formations continuously release some of their constituents. Estimates suggest that several tons of matter could escape every second, although this quantity varies depending on the methods used. To obtain these figures, direct observations from probes are compared to measurements taken from Earth. These cross-referenced data provide a more detailed glimpse of the phenomenon and hint at the potential disappearance of the rings if no sources replenish them. possibility of the ring's disappearance on a geological scale still divides specialists. Some argue that in a few 100 million years, Saturn might no longer display its iconic structures, resembling a giant devoid of adornment. Others remind us that natural events like moon disintegration or the capture of icy objects could prolong their existence. Regardless of the outcome, this awareness, reinforced by Cassini's data, encourages continued study of these unique formations in our solar system. The measurements taken between 2018 and 2021 were crucial for estimating the flux of matter leaving the rings. Between 2022 and 2023, a new era of Saturn observation opened for astronomers thanks to the James Webb Space Telescope. Designed to capture infrared light, this state-of-the-art instrument provided an unprecedented view of the ringed planet. The goal, to understand how this radiation, invisible to the human eye, interacts with Saturn's atmosphere and the particles that make up its rings. By exploring these wavelengths, researchers can now detect previously elusive phenomena, reveal the chemical composition of clouds, locate high-altitude ice, and measure pole temperatures. So much information has suddenly become accessible, opening a new window on the very nature of this planet and its environment. On June 25, 2023, a highlight marked the scientific community. The first image of Saturn taken by the telescope was unveiled, showing a surprisingly dark planet encircled by dazzling rings in infrared. In this image, Saturn appears as a darkened disk, quite different from the familiar pale yellow observed in visible light. This particular rendering, due to the weak emission and reflection of infrared, strongly contrasts with the intense brightness of the rings. Their brightness is explained by their composition, mostly made of water ice, mixed with dust and other materials. In this spectrum, the ice reflects light remarkably well, making the rings spectacular. The grains of ice capture and reflect infrared, creating the illusion of a luminous halo around the planet. For many, this striking contrast between the planet and its rings can be surprising. The traditional image of a golden Saturn with whitish rings shatters with this new view. The chemistry of gases and the nature of the surfaces give a completely different face to the planet. Scientists exploit this vision to study the molecules that absorb or scatter light depending on the altitude, and to analyze how different regions of the rings reflect infrared. This data allows for mapping the aerosols and gases present in the atmosphere, providing valuable insights into the internal circulations and large-scale meteorological dynamics. Among the significant discoveries is the presence of ice clouds more than 100 kilometers or 62 miles above the main layers. Invisible in visible light, these formations appear clearly in infrared. They testify to atmospheric movements capable of propelling water vapor to extreme altitudes where it condenses into ice crystals. These updrafts transport gases to colder regions where clouds then form. Studying these mechanisms helps to better understand how energy and matter circulate between Saturn's warm depths and its cooler upper layers. The telescope also allowed for mapping the temperature of Saturn's poles. This operation consists of measuring the heat emitted by each zone to deduce its temperature. A major challenge, since the north pole of the planet hosts a unique structure, a hexagon-shaped pattern. Infrared data makes it possible to analyze the temperature inside and outside this formation to assess the differences and compare them with other latitudes. These observations aim to identify atmospheric circulations specific to polar regions. The sensitivity of the James Webb Telescope instruments makes these readings particularly precise. Researchers study temperature variations to understand how internal heat escapes into space and how Saturn's rapid rotation influences this distribution. These measurements also allow for tracking seasonal changes, as with its 29 Earth-year revolution, Saturn experiences long and contrasting seasons. This new infrared vision enriches previous observations in visible or radio light, offering a more complete picture of the planet's atmospheric dynamics. Another major point of interest lies in what researchers call the infrared ring harvest, a term that reflects the richness of details now visible on these iconic structures. The rings, already famous for their fineness, reveal here subtle patterns, variations in brightness, and revealing contrasts. Some areas reflect infrared very efficiently, indicating a strong presence of pure ice. Others, darker, suggest a more dusty or organic material-rich composition. These differences provide clues about the formation, evolution, and interaction of the rings with the planet. Researchers also use these images to map the density and thickness of the rings at different distances from Saturn's center. Infrared detects sparsely populated or densely packed particle zones invisible otherwise. Each ring, designated by a letter, has its own characteristics. These details help to understand what mechanisms govern their evolution and the role of moons in their structuring. Some, called shepherds, exert gravitational influence that confines particles, drawing clear limits and causing undulations within the ring. The choice of June 25, 2023, to publish these images was not coincidental. It coincided with a favorable alignment and optimal orientation of the James Webb Telescope installed at the Lagrange point L2. The goal was also to test its ability to capture infrared light on an object as bright as Saturn, while maintaining a strong contrast with the rings. The results obtained herald numerous discoveries to come, as analysis techniques are refined. For the public, these images offer a fascinating dive into an invisible universe. Comparing a visible light photo to an infrared one reveals how our perception reflects only a tiny portion of reality. Colors, textures, and intensities change according to the wavelength, transforming our understanding of the cosmos. But these images are not just an aesthetic spectacle, they reveal major physical and chemical processes, otherwise invisible, that shape the evolution of gas giants. The recently observed ice clouds raise many questions. What is their exact composition? How much gas, like ammonia, reaches these altitudes? How does the temperature drop so high in the atmosphere? These elements directly influence the formation of winds and storms. Saturn's rapid rotation, combined with its flattened shape, contributes to unique circulation patterns, very different from those on Earth. These data will fuel the theoretical models of tomorrow. The thermal mapping of the poles also aims to solve a puzzle. How do the atmosphere and internal structure interact to maintain marked temperature differences? The telescope's infrared images reveal sensitive thermal variations according to the approach of the poles. Researchers are trying to link them to the presence of atmospheric jets, wave dynamics, and planetary rotation. Old telescopes had already identified a jet stream around the hexagon, but infrared now offers a better understanding of its depth and composition. To analyze these data, the telescope team relies on comparisons with past missions and numerical simulations. these atmospheric and structural models are confronted with real measurements to refine hypotheses. For example, on the composition of the rings, what is the purity of the ice? What part of dust is trapped in them? How many collisions between small moons contribute to their evolution? The 2023 images, combined with those obtained in visible light, will help answer these questions. Similarly, identifying high-altitude ice clouds can open new avenues on the mechanisms of evaporation and condensation of water. The rings, so radiant in the infrared, also become a tool for studying cosmic dust. Saturn receives a constant flow of micrometeorites and interstellar grains that can alter the surface of the crystals. The observed brightness variations help estimate the rate of contamination or erosion of the particles. In the long term, these measurements could indicate the age of the rings, a central question in theories about the formation of the solar system. This first assessment promises many observations to come. Astronomers plan to exploit the seasonal variations of polar lighting to study how the atmosphere reacts to the planet's tilt. Thanks to the infrared, they will be able to compare Saturn's states at different times, detect changes in cloud bands or rings, and better understand the planet's internal dynamics. Finally, for the general public, these infrared views provide a unique emotion while illustrating the power of current technology. Space is not limited to visible colors. It holds wonders revealed by different perspectives. This harvest of images does not just captivate. It unveils the very texture of the rings and reveals unsuspected clouds, signs of a dynamic atmosphere. Each measurement, each nuance, each contrast completes the grand puzzle of the solar system. Saturn, with its mysteries and beauty, remains one of the most fascinating celestial bodies. Between 2022 and 2023, the James Webb Space Telescope marked a decisive milestone. It allowed researchers to unveil some of the mysteries that still cluttered the understanding of the ringed planet. While it raised new questions, it also offered fertile ground for future explorations. For now, near-infrared reveals a long-hidden universe. We are only beginning to glimpse the complexity of Saturn. But this harvest of images and these perched clouds will surely open an exciting new chapter in space research. Between 2023 and 2024, Saturn offers astronomers around the world a rare opportunity to delve deeper into the secrets of its internal rotation, its mysterious polar hexagon, and its peculiar seasons. Imagine yourself in distant orbit, suspended in an almost absolute silence, as the immense gaseous choreography of a planet unfolds before your eyes, far beyond what we might conceive on Earth. In this cosmic tranquility, you follow the cloud bands that sweep from the equator to the confines of the atmosphere, where this curious phenomenon hides, the hexagonal jet. This jet refers to an atmospheric current of astonishing speed, describing a shape of remarkable precision, a hexagon. For several decades, scientists have tried to understand how such a figure can be maintained for so long, sometimes over hundreds of Saturnian years. The first clear images of this phenomenon date back to the 80s, thanks to the Voyager probes. Since then, numerous instruments have studied it from every angle, measuring wind speeds, cloud temperatures, and analyzing its chemical composition. Between 2023 and 2024, researchers continued this meticulous work, combining data gathered from Earth with the still unexplored findings of the Cassini mission. Their goal: to unravel the mystery of the planet's internal rotation, a complex task in the absence of a solid surface, unlike what we observe on Earth. The internal rotation refers to the movement of Saturn's deepest layers, mainly composed of hydrogen and helium, as well as its core. This rotation directly influences atmospheric dynamics and notably the stability of the polar hexagon. Yet, accurately defining this period has long been problematic. Initial measurements, derived from radio emissions captured by Voyager, suggested an approximate duration of about 10 hours, but results varied. Saturn's magnetic activity did not always match the actual rotation, leaving estimates uncertain. In this context, a recent study published in Geophysical Research Letters sheds new light. Relying on recent observations and complex hydrodynamic models, researchers conclude that Saturn's internal rotation is approximately 10 hours, 33 minutes, with a margin of 15 seconds. This advance allows a better understanding of why different methods yield such fluctuating results. Thanks to the remarkable stability of the hexagon, which seems decoupled from external disturbances, we finally have a reliable benchmark. The hexagon is thus not merely an atmospheric curiosity, but a visible indicator of the planet's deep function. To better apprehend this structure, imagine a vast wind corridor several thousand kilometers or miles wide, rotating at several hundred meters per second, or about 1,000 feet per second, around the North Pole. This corridor folds onto itself, forming 6 sharp angles, creating an almost perfect hexagon. On our scale, this seems improbable. Yet, laboratory experiments have shown that such shapes can emerge when a fluid rotates rapidly in a cylinder. Saturn then acts as a natural laboratory, and the longevity of its hexagon proves that internal dynamics constantly feed this intense current. In 2023, new observation campaigns rely on very high-resolution terrestrial telescopes and infrared imaging to scrutinize the invisible layers beneath the clouds. It is discovered that the temperature at the top of the polar layer can drop to minus 190 degrees Celsius, or about 310 degrees Fahrenheit, contrasting with the more temperate equatorial regions. These thermal gaps help refine models explaining the hexagon's stability, since temperature directly influences gas density and wind speeds. But beyond the rotation, the year 2024 is also shaping up as a key moment to understand Saturn's seasons. With an inclination of 27 degrees and an orbit of 29 years around the Sun, the seasons there last about 7 years each. Observing the color variations of the North Pole over time is thus to follow a large-scale climate evolution. In summer, the clouds evaporate, sometimes revealing golden or bluish hues. In winter, the opposite hemisphere plunges into shadow, further accentuating the thermal contrasts. Another spectacular event is being prepared for the end of 2025, the alignment of Saturn's rings. By then, their plane will be almost aligned with our line of sight. As a result, the rings will appear almost invisible from Earth. This rare phenomenon, often compared to a magic trick, gives the impression that the rings have disappeared. In reality, they are still there, but their thinness, sometimes just a few tens of meters or about 100 feet, makes them imperceptible to the naked eye when viewed edge-on. This moment, as astonishing as it may be, offers a unique opportunity to observe the planet without the light reflected by its rings. Researchers intend to exploit this configuration to measure more precisely the brightness reflected by Saturn itself. Such geometry allows refining estimations of the atmospheric composition without visual interference. For astronomy enthusiasts, this temporary disappearance might seem frustrating, but it will take little time before the tilt changes and the rings reappear in all their splendor. This cycle of disappearance and return occurs about every 15 years, depending on Saturn's position in the sky. What we will experience between the end of 2025 and the beginning of 2026 is thus simply a step in a long celestial cycle. All these phenomena, I mean the refined measurement of rotation, the persistence of the hexagon, and the alignment of the rings, fit into a rigorous schedule revealing the mechanical beauty of the cosmos. Studying Saturn is not only about admiring a spectacular planet, it is also about understanding the physical processes that govern gas giants, including those orbiting distant stars. In this sense, the period spanning from 2023 to 2024 marks a turning point. We are still close to the end of Cassini, but already at the dawn of new missions. It is an essential transition phase. Analyzing this data lays the foundation for discoveries to come. Better understanding internal rotation allows us to specify Saturn's deep structure. Studying the hexagonal jet provides insight into convection movements inside this gigantic world. As for the change in orientation of the rings, it reminds us that nothing is fixed in the universe. For the general public, it is also an opportunity to look up at the sky. Until the end of 2024, the rings remain visible from a still favorable angle. It's the ideal time to point even a modest telescope at this celestial wonder. And as the alignment moment approaches, you will gradually notice their thinning until they almost completely disappear. This phenomenon is not a loss, but a scientific opportunity. Without the reflecting effect of the rings, astronomers can better estimate the planet's albedo. These variations in light, month after month, offer an unprecedented glimpse into the chemistry and dynamics of the upper atmosphere. At the same time, any change in the hexagon's activity, be it a shift, strengthening, or weakening, will allow us to verify the validity of the estimated internal rotation period. Even slight discrepancies could reveal that this period is not as stable as previously thought. From Earth, we may only see a distant globe streaked with cloud bands. Yet, what we are observing is a complex tale, composed of rotation, chemistry, gravity, and light. Whether it's the hexagon revealing Saturn's internal rhythm or the rings temporarily fading away, 2024 reminds us that only patience allows us to grasp the cosmos's subtleties. Each advance around Saturn illuminates a bit more the diversity of worlds surrounding us. And as exploration of our solar system progresses, these discoveries enrich our understanding of planets located far beyond our horizon. Thus, this key period between 2023 and 2024 embodies the meeting point between research, dreams, and contemplation. On one side, the knowledge of Saturnian time is refined. On the other, we witness a spectacular visual transformation. In less than 2 years, two essential pieces of the Saturnian puzzle come together: the exact duration of a day within the planet's depths and the real demonstration, before our eyes, that its grandiose rings can almost completely disappear depending on their orientation. That is why the study of Saturn exceeds mere scientific interest. It becomes an intellectual and sensitive quest, a step further towards understanding giant worlds and the universe surrounding us. Throughout the year 2024, the scientific community experienced unusual excitement around the planet Saturn. The missions of the Cassini probe, which concluded a few years earlier, had already highlighted the fascinating complexity of the debris rings surrounding it. But several research teams explored a new avenue. According to Japanese scientists who published their findings in the journal Nature Geoscience, these rings could be much older than previously imagined, while presenting an astonishingly young appearance. This paradox could be explained by a phenomenon called self-cleaning, linked to the sublimation of particles following multiple impacts with meteorites, cosmic dust, or other fragments from space. To understand this mechanism, one must first grasp what sublimation is. It is the direct transition from a solid to a gaseous state without passing through a liquid phase. In Saturn's icy rings, this means that, due to repeated collisions and heat, part of the ice transforms into vapor and disperses, thus preventing the accumulation of impure matter. This process would act as a natural cleaning, maintaining the ring's brilliance, while gradually eliminating the traces left by impacts of darker or mineral-laden bodies. Relying on advanced computer simulations, the Japanese researchers reconstructed what could have been Saturn's history over several billion years. At the dawn of the solar system, enormous quantities of ice and dust orbited around the planet. This initial period would have seen frozen blocks, rocky fragments, and massive bodies collide, forming a gigantic debris disk. Gradually, solar radiation, asteroid or comet impacts, and Saturn's gravitational pull would have acted as filters. The purest particles would have persisted, while the darker, contaminated ones would have sublimated over time. This hypothesis challenges the widely held idea that the rings appeared recently, perhaps from the collapse of a moon or an icy object. Those who support this more recent version rely on the apparent mass and brilliance of the rings, which seem to indicate an age of a few 100 million years. But the new Japanese model argues that these measurements do not account for the ongoing role of sublimation, capable of maintaining a clean appearance while concealing an origin dating back over 4 billion years. Such antiquity would fundamentally alter our understanding of the primitive solar system. Theoretically, if these rings indeed date back to the early days of the solar system, they would offer a unique window into its initial stages. When the sun formed from a cloud of gas and dust, the planets emerged from this swirling rotation. If Saturn preserved some of this icy matter in the form of rings, then this disk could contain crucial clues about the initial presence of water, organic compounds, or minerals. Such a hypothesis paves the way for new research aimed at identifying ancient chemical signatures and illuminating the distant history of our cosmic environment. But this view is not unanimous. Some scientists recall that observations from the Cassini probe have shown the efficiency of the rings in eliminating debris entering Saturn's sphere of influence. Furthermore, the phenomenon called ring rain, which corresponds to particles falling into the planet's upper atmosphere, indicates a precipitation rate that might have already eroded these structures if they were that ancient. However, proponents of the Japanese model believe that the transfer of matter could be much more complex, and that interactions with Saturn's magnetosphere would contribute to their preservation over very long periods. In their publication relayed by AP News, the authors emphasize the effect of micro-impacts. Even tiny dust grains moving at very high speeds can chip away ice fragments or melt the surface of ring particles. This heat, although slight, accumulates over immense periods, leading to a slow transformation of ice into vapor. This water vapor, as it disperses, carries away the embedded impurities, such as dark residues from meteorites or carbon-rich molecules. Dynamically, the article also suggests that resonance mechanisms may have evolved over time. Zones that were once chaotic, tangled with intertwined particles, might have gradually flattened, giving the rings a more uniform appearance. This evolution would have altered the mass distribution, affecting the orbital speed of certain segments. Researchers thus think that some zones have almost completely vanished, while others have become denser, preserving the overall structure. For planetary formation specialists, these ideas might rewrite part of the history of the solar system. If the rings indeed took shape shortly after the birth of the planets, they would have survived a succession of upheavals: comet passages, asteroid impacts, fluctuations in solar activity, and possibly even the gravitational migrations of the gas giants. In this perspective, the self-cleaning mechanism becomes crucial in explaining how this disk has withstood so many violent events while maintaining a brightness once thought to be associated with youth. For many, this hypothesis represents a major advancement, potentially transforming our research on Saturn and the origin of icy worlds elsewhere in the universe. Because if one seeks to compare this phenomenon to other known cases, no other giant planet possesses such an extensive and luminous ring system. Neither Jupiter, Uranus, nor Neptune offers such a spectacle. Studying this exceptional ring thus constitutes a rare opportunity to test scenarios applicable to other stellar environments. According to Japanese researchers, everything would depend on a subtle balance. Sublimation, slow enough not to destroy the ice, but sufficient to dissipate impurities. Other planets might have seen their primitive rings disappear due to a too rapid rate. The consequences of this mechanism on our view of the early solar system are immense, demonstrating that such a disk can survive for several billion years while remaining radiant pushes us to rethink our models. These works reinforce the idea that a fragile balance among impacts, gravity, and sublimation durably shapes the environment around giant planets. In this year, 2025, an unexpected revelation is overturning our perception of the solar system. For decades, Jupiter dominated the scene with the most moons orbiting a single planet. But March 11th, 2025 marks a turning point. Saturn regains the lead in the ranking with the official addition of 128 moons recently identified, validated, and recorded by the Minor Planet Center, or MPC. This spectacular leap brings the total number of Saturn's satellites to 274, thus significantly surpassing its eternal rival. For many, this announcement inaugurates a new chapter on orbital dynamics and the incredible diversity surrounding Saturn, long admired primarily for its rings. But beyond the numbers, it is especially the detection techniques and the scientific outcomes that stimulate researchers' interest and animate exchanges within the astronomical community. Discovering new moons often evokes the image of a solitary astronomer observing a luminous point through a telescope. The modern reality is much more sophisticated. Current observation methods rely on powerful telescopes positioned in strategic locations, often at high altitudes, to benefit from optimal atmospheric conditions. This is the case with the Subaru telescope, located at the summit of Mauna Kea in Hawaii. This international-grade instrument is equipped with ultra-precise sensors and optical devices that allow the exploration of vast portions of the sky. The images obtained are then analyzed using advanced digital processing, and this is where a key technique comes into play: shift stack. This method involves taking a series of shots of the same area of the sky at close intervals, and then combining them by compensating for the potential movement of distant objects. To explain it simply, imagine a nighttime scene where a firefly moves very slightly from one photo to the next. Superimposing these images without correction makes it blurry or appears as a streak. However, by adjusting each image based on the movement of the firefly, its glow becomes clearer. This same principle applies to the search for distant moons. By calculating the probable trajectory, astronomers can align the images with their orbital movement. The The result is striking. Even the most discrete objects become visible in the final image, whereas they would have escaped any individual detection. It is thanks to this approach that dozens of new moons have been confirmed around Saturn. The researchers involved, notably those linked to the Subaru Observatory, spent long months combing through countless sequences of images. They tracked, compared, filtered, and verified each trajectory to ensure they were indeed Saturn's satellites and not mere celestial passers-by. At the end of these investigations, the Minor Planets Center validated the existence of 128 additional moons. The announcement quickly circulated in the scientific world, confirming that Saturn's vicinity is much more populated than previously imagined. The decisive moment came when the MPC, responsible for registering minor celestial objects, published a circular officially recognizing these 128 new moons. The total now reaches 274 bodies, mixing well-known large moons like Titan or Enceladus, with a multitude of satellites of irregular shapes and orbits. These latter ones, often having elongated or inclined trajectories, could have been captured by Saturn's gravity rather than formed in situ. Some might even be fragments of an ancient moon destroyed during a violent collision. This fragmentation hypothesis is fueling many theories today about the origin of moons and their possible link to the chaotic history of the planet's rings. This discovery reinforces the idea that Saturn constitutes a veritable natural laboratory for studying small orbiting bodies. Experts in celestial mechanics, specializing in the analysis of planetary movements, are closely examining the arrangement of these trajectories to assess their stability. In such a dense system, cluttered with debris and particles, a question persists. How do these moons manage to remain in orbit without being expelled or absorbed by the planet? The study reveals the existence of orbital resonances, where certain moons or particles synchronize their revolution in simple ratios, like 2-to-1 or 3-to-2. These resonances can stabilize the system in the long term, but also cause upheavals if a new object disrupts the balance. The notion of slow collision of ring fragments refers to a process in which the particles constituting Saturn's rings, ranging from dust to blocks several meters or yards across, interact due to gravitational and electrostatic forces. Over time, some fragments aggregate and grow large enough to form small satellites. These collisions occur at low speed, favoring cohesion rather than fragmentation. Conversely, a fragile moon can break apart after an impact, instantly reintroducing debris into the ring. These mechanisms of aggregation and destruction contribute to the increasing complexity of Saturn's environment. The new record set by Saturn also raises questions about the origin of its moons and rings. Some suggest that it may have captured ancient bodies from the outer system, rich in ice and primitive materials. Others believe the rings themselves could be the remnants of dismantled former satellites. Thanks to increasingly precise observations, it is becoming possible to trace part of the history of Saturn, its satellites, and more broadly, the formation of the outer solar system. Beyond simple enumeration, this discovery enriches our understanding of planetary systems. The coexistence of hundreds of moons around a gas giant implies complex interactions capable of redistributing orbital energy. Some moons may be ejected to the far reaches of the system. Others may fall toward the planet or collide with a ring. Analyzing these trajectories helps to better understand the mechanisms at work in the formation or destruction of satellites, knowledge that can be applied to recently discovered giant exoplanets. The study of these complex orbital architectures also helps to better grasp the conditions that could make a remote system habitable. To follow the evolution of these moons, numerical simulations are conducted. Researchers model the chaotic interactions of a swarm of irregular satellites, often with elongated and inclined trajectories. With the addition of 128 moons, these models must be adjusted to account for their characteristics: size, estimated density, risks of collisions, even low ones. These simulations reveal trends. Does the system tend to stabilize? Will it reach a critical density threshold leading to multiple collisions? Or will these moons continue their peaceful orbit for millions of years? Beyond pure mechanics, the public is often fascinated by the idea that these small bodies could become exploration targets. Although most of them are tiny, often on the scale of a city, their observation could yield valuable clues about the chemical composition of their environment. Each moon, orbiting Saturn, represents a potential sample of the primordial matter of the solar system. Their surface, their ability to reflect light, or the spectral signature of their minerals are all elements that help to better understand their origin. Some seem to originate from distant regions like the Kuiper Belt, or even the vicinity of Neptune, while others appear formed locally, composed of ice, silicates, and carbonaceous materials. The rivalry between Jupiter and Saturn over the number of moons may seem trivial or anecdotal, but it actually illustrates the richness of ongoing research. Methods such as shift stack will be perfected, likely revealing even smaller, darker, or more distant objects. Nothing prevents one from imagining that other telescopes or new techniques will redistribute this title in the future, perhaps even to Uranus or Neptune, if this hunt is pursued with enough tenacity. At the pace of technological advances, each gas giant could well reveal its own secrets, hidden in a tiny glow in a deep sky image. But today, it is indeed Saturn that steals the spotlight from Jupiter. The official announcement of these 128 new moons on March 11th, 2025, has captivated the media and reaffirmed the mystery surrounding the ringed planet. The scientific community is now focusing on this network of orbits and the future of this expanded family. The notions of stability and slow collision impose themselves as keys to understanding how the combined gravitational forces of Saturn, its major moons, and its rings durably influence these trajectories. And on a larger scale, these discoveries enrich our understanding of the dynamics at work in other planetary systems. The prospects are numerous. Some suggest observing the debris surrounding the latest moons discovered, looking for signs of aggregation or, conversely, fragmentation. Others envision dedicated missions capable of flying over these moons and collecting samples for on-site analysis. Although complex and costly, such expeditions could provide spectacular information on the composition of these mini-satellites and the processes that shape this very particular environment. At the beginning of the year 2025, researchers' attention is once again focused on Titan, Saturn's largest moon. In specialized laboratories, scientists are conducting an ambitious experimental campaign to uncover the secrets of its complex atmosphere. Titan has long fascinated scientists due to the predominance of diatomic nitrogen, a gas also present in Earth's atmosphere. However, this concentration results from a fragile balance maintained by chemical mechanisms that are still not well understood. On January 27, a publication relayed by the site Science Daily highlighted the key role of methane photolysis in the long-term stability of diatomic nitrogen. To explore this phenomenon, researchers are trying to recreate in the laboratory the extreme conditions that prevail on Titan. Methane photolysis corresponds to the decomposition of its molecules under the effect of ultraviolet radiation emitted by the sun. On Titan, this light passes through the upper atmosphere, triggering a series of reactions that release free radicals capable of forming new compounds. This chemical cascade contributes to the creation of more complex structures, such as certain hydrocarbons or elements of organic chemistry. Recent studies reveal that this process actively participates in the retention of diatomic nitrogen. To test this hypothesis, researchers use vacuum chambers and light sources simulating solar radiation. These installations replicate the low-pressure characteristic of Titan's upper atmosphere and allow for the introduction of gas mixtures in realistic proportions. By exposing them to a calibrated light, scientists monitor chemical evolution using high-precision spectrometry tools. The first data, already released in preprint, suggests that methane photolysis leads to a series of secondary reactions involving elements such as hydrogen, carbon, and nitrogen. The result is increasingly elaborate chemistry, reinforcing the idea that Titan might contain some of the fundamental ingredients for the origin of life. In parallel, another series of experiments is focusing on Enceladus, an icy moon of Saturn, known for its spectacular jets of vapor and particles originating from its southern polar region. Unlike terrestrial volcanoes, Enceladus's cryovolcanoes eject salty water, dissolved minerals, and possibly even organic compounds. To understand the internal processes of this moon, researchers have reproduced its underground conditions in the laboratory, in cryogenic chambers capable of reaching temperatures below 200 degrees Celsius or 328 degrees Fahrenheit. In these simulated environments, temperature and pressure are finely adjusted. Water enriched with mineral salts is injected under layers of ice, causing cracks as it crystallizes. Gradually, miniature geysers emerge, releasing substances similar to those detected by probes around Saturn. Phosphates in particular are closely scrutinized as they play a central role in the mechanisms of life, notably in the formation of DNA and RNA. Their presence in these simulations supports the idea that Enceladus could harbor an environment favorable to the development or conservation of elementary life forms. The preliminary results support the hypotheses made by previous space missions. The Cassini probe, after more than 10 years of observations, revealed samples rich in nutrients. Recent laboratory experiments now allow us to concretely understand how water, salts, and phosphates can coexist and persist in an underground world. By simulating the pressure exerted by the ice, researchers observe how the liquid rises to the surface through natural conduits, giving rise to plumes comparable to those of Enceladus. These discoveries support the idea that beneath its frozen crust, this moon harbors a warm and humid zone with remarkable astrobiological potential. Another significant aspect of this work concerns the possible formation of complex organic molecules under extreme conditions. When water comes into contact with salts and undergoes significant temperature variations, prebiotic reactions can occur. Chemists engaged in the project have observed the formation of short carbon chains, which could precede more sophisticated structures such as amino acids. Although these results are still at the theoretical stage, simulations show that the presence of phosphates, combined with hydrothermal gradients, creates a reactive environment. These mechanisms are reminiscent of those that might have existed in Earth's primordial oceans. Taken together, the results obtained on Titan and Enceladus offer two distinct but complementary fields of study. On one hand, there is a dense atmosphere dominated by nitrogen and a methane-based hydrological cycle. On the other, there is a global ocean buried under ice, likely in contact with a mineral core. Research on the stability of nitrogen on Titan and simulations of cryovolcanism on Enceladus enrich each other. By analyzing the chemical reactions specific to each environment, scientists refine their understanding of the conditions conducive to the emergence of life. The laboratories involved plan to expand their protocols by incorporating new factors. The presence of ammonia, potentially buried in the depths of Enceladus, could alter the freezing point of water and maintain a more stable liquid environment. On Titan, organic aerosols present in the upper layers of the atmosphere also attract interest. Carried by winds and then deposited on the ground, these particles could enrich the surface with carbon compounds, especially at the points of contact between the ice and a possible internal ocean. Each variable introduced complements our global vision of chemical dynamics in the Saturnian system. January 27, 2025, thus marks a milestone in the study of planetary chemistry. Discoveries on methane photolysis and simulations of Enceladus's cryovolcanoes provide new insights into conditions that might favor an ecosystem beyond Earth. Researchers emphasize the troubling parallels with primitive Earth. Between gas retention and the presence of underground water, these worlds offer varied paths leading to habitable contexts. In 2025, science continues to progress in exploring the worlds hidden in Saturn's icy shadow. In this 12th stage of our journey through the exploration of Saturn and its moons, the focus now shifts to space programs shaping the future of planetary research. In March 2025, the National Space Agency confirmed, as part of the federal budget, official support for the Dragonfly mission scheduled for launch in July 2028. Meanwhile, teams are continuing their work on a project named Enceladus Orbalander, included in the proposals for the next wave of New Frontiers missions and under study since 2024. These initiatives, going through stages of technical validation and economic evaluation, herald the advent of a new scientific era centered on Titan and Enceladus, two major moons in our quest for potentially habitable worlds. Enthusiasm is growing among researchers as the prospects for discoveries challenging our view of life are numerous. Dragonfly, supported by these funds, will be dedicated to the in-depth study of Titan, Saturn's largest moon. Since the arrival of the Huygens module in 2005, Titan has sparked increasing fascination thanks to its dense atmosphere, composed of nitrogen and methane, its liquid hydrocarbon lakes, and its vast fields of dunes. Dragonfly will take the form of a multi-rotor drone, capable of moving nimbly from site to site, thanks to low gravity and a thick atmosphere. This flying capability will allow access to a diversity of terrains, perform ground sampling, analyze the chemistry, and create a finer map of the surface. The objective is clear: to better understand the mechanisms of prebiotic chemistry in this unique environment. To achieve this goal, Dragonfly will carry a range of state-of-the-art instruments. A mass spectrometer will be responsible for detecting organic molecules, while a set of geophysical sensors will examine the internal structure of the moon. The craft will be powered by a radioisotope thermoelectric generator, ensuring stable energy despite the low sunlight. Engineers will nevertheless have to face the extreme conditions of Titan, where temperatures drop to nearly 180 degrees Celsius or 292 degrees Celsius. Adapted thermal systems will be essential to ensure the drone functions properly. If the schedule is met, the landing could take place in the early 2030s, marking the launch of a mission that is set to last several years and deliver crucial data. At the same time, the other major ambition concerns Enceladus, this icy moon with spectacular geysers revealed by the Cassini mission. The Enceladus Orbilander project, currently in its initial study phase, aims to design a craft that combines extended orbit and landing capability. Enceladus attracts attention because it harbors a liquid ocean beneath its frozen crust, kept in motion by tidal forces. The jets emitted into space contain water vapor, organic compounds, and salts, all clues suggesting an environment favorable to the emergence of life or advanced chemical reactions. The Orbilander concept blends two strategies: extended observation from orbit to study the global geology and active zones, then a descent to land on the ice. Once on the ground, the craft could collect samples from regions near the polar fractures. Analytical instruments, such as a high-precision spectrometer, would be responsible for detecting potential biomarkers and measuring the complexity of present molecules. This data would also clarify the mechanisms behind the plumes and help understand the internal movements of this fascinating moon. Technically, this mission represents a major challenge. Unlike Titan, Enceladus does not have a sufficient atmosphere to cushion the descent, which requires a particularly reliable propulsion system. The icy and rugged surface requires a lander capable of stabilizing in an unpredictable environment. Exposure to radiation and temperature fluctuations demands extremely resistant materials. In orbit, the apparatus will also have to navigate precisely to fly over the geysers and collect particles without risking a collision. Each trajectory will have to be carefully calculated, mobilizing all the expertise of space dynamics specialists. From a scientific point of view, the Orbilander could provide decisive answers about Enceladus's subsurface chemistry. Since the detection of simple organic molecules in the icy jets, researchers have wondered about the possibility of finding primitive life forms there, similar to those in Earth's abyssal depths. The indications converge. The presence of water, salts, heat, and energy creates an environment conducive to complex reactions. An on-site mission would allow us to assess the real scope of these processes and determine how far chemistry can go in a world isolated beneath the ice. To realize this ambition, the current phase involves close collaboration between agencies and laboratories. Teams are considering equipping the mission with mini-drills capable of reaching deeper layers and are contemplating the organization of scientific operations despite transmission delays of more than an hour. The New Frontiers program, in which this project is involved, remains highly competitive. Several concepts are under study, each aiming to meet the priorities defined by scientific plans. If Enceladus Orbilander is selected, it could enter the formal development phase in the coming years. Dragonfly and Orbilander are part of a broader dynamic of exploring the oceanic worlds of the solar system. After the moons of Jupiter, it is Saturn's system that takes center stage. The budget voted in March 2025 demonstrates a clear commitment to ambitious missions, capable of transforming our understanding of habitability. Dragonfly, through its flights in Titan's orange skies, and the Orbilander, through its investigations on Enceladus's ice, offer two complementary approaches to answering fundamental questions. These projects also serve as testing grounds for future technologies, which could one day lead us to other worlds far beyond our system. In the short term, the challenge remains to pass through all the critical validation stages before entering the construction phase. Dragonfly, already well advanced, is still aiming for a launch in July 2028. The Orbilander will still need to demonstrate its full feasibility to hope to move to the next phase. If these projects succeed, their results could redefine our vision of life in the cosmos, revealing active chemical processes on other worlds and exploring the thin boundary between geology and biology. the image of a drone hovering over the plains of Titan or a lander probing the icy depths of Enceladus already embodies the next generation of space exploration, resolutely focused on the submerged worlds. The next major steps in the exploration of Saturn, scheduled between 2026 and 2035, mark a decisive phase for deepening our understanding of the giant gas planets and the small bodies of the solar system. This decade will see the convergence of space projects and terrestrial observation instruments around several key issues: monitoring the ring rain, refining the mapping of structures orbiting the planet, and comparing Saturn to similar exoplanets. It will involve deciphering the mechanisms at work in these spectacular worlds, relying on technological innovations and the synergy between local data and distant observations. Among the most anticipated missions is a compact craft named Rexus Saturn CubeSat. This small satellite of reduced format is designed to carry various experiments upon its insertion into orbit around Saturn. Its name, inspired by an X-ray imaging system, may vary according to the institutions involved. The ride-share approach means it will be launched alongside another main mission, thus sharing the same launch vehicle. This method allows resources to be optimized and significantly reduces the costs of reaching such a distant target. The primary goal of the Rexus Saturn CubeSat will be to observe a phenomenon known as ring rain. This is the gradual descent of particles, originating from Saturn's rings into the upper layers of its atmosphere. This rain is unlike anything we know on Earth. It is composed of eroded ice and dust fragments that eventually dissipate into the planet's gaseous heights. Following this process in detail will enable the estimation of the wear rate of the rings and help to better ascertain their age. If this loss turns out to be faster than anticipated, it could mean that Saturn's majestic rings are far more ephemeral than previously imagined. To identify the chemical components of this rain, the CubeSat will be equipped with sensors capable of detecting different types of radiation. These instruments will measure the energy diffused or absorbed by the ice particles and interacting gases. With this data, researchers can determine the proportions of frozen water, hydrocarbons, and other complex elements integrated into the ring's structure. These findings will complement information from previous missions and contribute to clarifying the formation and evolution mechanisms of the Saturnian system. In parallel, several very large terrestrial telescopes, some exceeding 30 meters or 98 feet in diameter, are under construction or enhancement. Equipped with adaptive optics, they will be able to compensate for the distortions caused by Earth's atmosphere and provide images of unprecedented clarity. Thanks to this precision, scientists will detect millimeter-scale density waves in Saturn's sea ring. These waves, comparable to fine ripples spreading across a lake, reflect the gravitational influence exerted by the planet and its moons on the ring's structure. The analysis of these density waves will provide valuable insights into the forces at play in the sea ring. By studying their speed and shape, researchers will refine their models of gravitational interaction between Saturn, its satellites, and the icy particles. This data will enhance our understanding of the cohesion mechanisms within the rings and the cycles of creation and disintegration that structure the entire planetary system. Terrestrial telescopes will complement orbital observations by offering broader wavelength coverage and prolonged temporal monitoring, ideal for detecting seasonal variations and external disturbances. Beyond Saturn, the advancements made around this planet directly influence the study of giant exoplanets. Scientists are particularly interested in warm Saturn-type analogs, planets located around other stars, whose mass and composition are reminiscent of Saturn, but at much higher temperatures. Their proximity to their star increases the intensity of radiation, which can affect the stability of the rings surrounding them. Understanding how these rings survive or disintegrate under local conditions is essential for assessing their presence in other systems. An important criterion for detecting such rings is stellar extinction, a decrease in brightness measured when the planet passes in front of its star. If this planet is surrounded by an extended ring, the dimming will be more pronounced. A detailed analysis of this decrease allows the deduction of the size, density, and nature of the rings. The models used to interpret these light curves are based on precise observations of Saturn. This planet thus serves as a reference for identifying the characteristic signals of giant rings in distant extrasolar systems. Another aspect of this research is based on high-resolution polarimetry, a method that involves measuring the orientation of light after diffusion or reflection. The way icy surfaces and dust grains alter this orientation provides insights into the composition and structure of the rings. For Saturn, this technique specifies the size and distribution of particles. Applied to exoplanets, it offers a way to calculate the mass of vast rings while exploring their origin and potential lifespan. In the years to come, these technical innovations and joint programs will redefine our understanding of gas giants, their complex rings, and their extrasolar equivalents. They will illuminate the mechanisms of planetary system formation in our galaxy, revealing the subtle links that unite matter, gravity, and light on cosmic scales.